In this video, we're going to look at some examples of differentiation in action. The classic example is for kinematics. Let's imagine that we have some situation like we've got on this graph on the left, where we've had some sort of motion, we've recorded that motion, and we know what the displacement does as a function of time. That's what this notation here means. And a graph of that displacement versus time produces a curve. On first glance, it might look quadratic, but let's say after doing some clever analysis, maybe we throw it at a very clever computer program, it tells us that the displacement is varying like this. Well, if that's the case, what's the velocity and what's the acceleration doing? Is this a case of uniform acceleration? Well, almost certainly not. So let's find out what the acceleration is doing. Now, when you get very good at spotting these sorts of things, you'll see this cube on the time for the displacement and recognize that this must mean there is a non-uniform acceleration. But if this graph was just a quadratic, well, that would be uniform acceleration. So just glancing at the graph isn't enough to be able to tell. We need an expression for the displacement as a function of time. We've got the expression for displacement here. So we use the rule that we looked at in the last video. Now, we're going to multiply this coefficient here by the power, and then we're going to reduce the power. And that gives us 3 multiplied by 1/30 is 1/10, and then the 3 reduces to a 2. So that's how we get this term here. A nice thing about differentiation is where an expression includes parts that are added or subtracted, we can handle those separately. So here's the second part, and again, we are going to multiply the coefficient by 2, which gives us 10, and reduce the power by 1, and that leaves us with the expression you can see here. Now, that is the velocity of whatever this situation is, whatever this body is that's in motion. This is the velocity. It is the first derivative of the displacement as a function of time. The second derivative of displacement is the first derivative of the velocity. And that's the definition of the acceleration. So let's differentiate the velocity. Again, we're going to multiply the coefficient by the power. So 1/10 becomes 1/5, and we reduce the power by 1. And the second term here, the 10 is multiplied by 1, so it stays as 10, and the 1 is reduced to 0. Well, anything to the power of 0 is just 1, so t to the power of 0 is just 1, so the t is just 1, so I'm not going to bother writing the number 1 there. And so here's our expression for acceleration, and you can see in this case the acceleration initially when t was 0, when this time here was equal to 0, the acceleration was 10 of whatever units we're using, 10 meters per square second probably. But then t increases from 0, and as t increases from 0, this reduces the acceleration. That's why there's a minus there. And in 5 seconds, the acceleration is reduced by 1 of these units. It is possible to work the other way and have an expression for acceleration and use that to calculate the displacement function, and that's called integration. We'll do that in a later video. So here's another example. This is looking at electric fields. Now, our equation for the electric potential, because of a charge, looks like this, where Q is a charge and R is some radial distance from that charge. So the potential at some radial distance from the charge is equal to this, where 4 pi epsilon naught is, well, 1 over 4 pi epsilon naught is all one constant. And we could rewrite that expression like this, and you can see we've got Q over 4 pi epsilon naught, that's all a constant, multiplied by R to the minus 1. And potential here is a function of R. R is the variable. The others are all constants. Now, sometimes we'll say field strength is the potential gradient. Actually, it's minus the potential gradient. So here is an equation showing potential gradient. The potential gradient, when potential is a function of R, is the first derivative of the potential with respect to R. So d by dr of that function of R. But again, it's got a minus here by definition. Now, if you substitute that function v, you end up with this. Now, you can see I've taken those constants to the left of that d by dr. And if you look at the expression up here on the top left, you can see why I've done that. The a doesn't really change by doing this differentiation. So you can factor the a out and do the differentiation without it. So q over 4 pi epsilon naught, or should I say minus q over 4 pi epsilon naught, is all a constant. So I've just moved that to the left of this derivative. And then we follow the same rules. So this minus 1 gets multiplied with all this to become plus. Remember, this is minus here, so we have a plus. And the minus 1, we reduce by 1, it becomes minus 2. So this is our expression for the electric field strength at a distance r from the charge q. Usually we wouldn't write it like this. We might tidy it up a little bit. So our electric field strength might look like this, but it's the same thing. And you can see that the electric field strength varies as the inverse square of the distance between the charge and the point where you're measuring that field strength. And there are a few examples within physics where we might need something a bit more exotic than this very straightforward way of differentiating. This works for polynomials. It doesn't work for trigonometry. So we're going to look at that next.